So we're talking about these letters. The subscript is going to tell us what term we're talking about. Okay? So A sub 1 to represent the first term, A sub 2 to represent the second term, and so forth and so on. So given the sequence 2, 5, 8, and 11, A sub 1 is going to be your first term. So A sub 1 is going to be 2. A sub 2 is going to be 5. A sub 3 is going to be 8. And then A sub 4 is going to be 11. So that subscript refers to what term you're talking about. And then the value of it is whatever is at that particular location. So it says write down the first six terms of the following sequence and then graph it. So if you look here, let's write out the first 6. So we're going to have A sub 1, A sub 2, A sub 3, A sub 4. Probably should give me some more room. So we're going to do the first 6 terms. Just so happens, N represents what term we are on. So, for the first term, N is going to represent 1. So, N equals 1 for the first term. So we plug it in, 1 minus 1 divided by 1. Well, that's 0 over 1, which is equal to 0. A sub 2 is N equals 2. So you plug it in. 2 minus 1 over 2, which gives us 1/2. And then you go on, the next one. We're just doing the same thing. All we're doing is taking the equation and plugging in what term we're on into the variable. So 3 minus 1 over 3, or 3 minus 1 over 3 is 2/3. 4 minus 1 over 4 is 3/4. Do you see a pattern that's going on now? If I don't have to plug in the rest, what do you see is happening? The denominator is increasing by 1. So what's the next one going to be? 5. What's the numerator going to be? 1 less. The denominator is going to be what term you're on. So this term is N equals 5. That's the denominator. The numerator is going to be 1 less than that. So it's 4/5. You're a little bit ahead, Sean. So what's going to be the last one?
Oh, I thought you were going there.
Yeah, that's okay. We're doing the next one. So the next one is, term is the denominator. 1 minus that's going to be your numerator. So after a while, you see the patterns, and you can go through and say, okay, there's what I see is going on along the way. And it's just plugging in a term number in for a certain variable. So let's scroll to here. Write down the first 6 terms of the sequence and then graph it. So let's go and look at this one. Now this one's got a little bit more, because it's raised to a power, right? So, and I don't have as much space, so I'll go ahead and say the first one, N equals 1. So A sub 1 is equal to, and we use the equation, negative 1 raised to the 1 plus 1 power times 2 over 1, and we simplify that. So, what is negative 1? Well, what's negative 1 raised to the squared? What's negative 1 squared? 1, positive 1. Times 2 over 1, what does that simplify to? 2. So the answer actually just ends up being 2. Now what happens if the n is equal to 2? So, same equation, but now it's 2 plus 1 over 2 over 2. 2 plus 1 is 3. What's negative 1 raised to the third power? Negative 1 times 2 over 2, which reduces to what? 1. Let's move on to...
Is it positive or negative 1?
It's negative. Negative 1 is always going to be raised to a power. This one is 2 divided by 2, and it's multiplied times negative 1 raised to the third power. Anytime negative 1 is raised to an odd power, it's negative. Anytime it's raised to an even power, it's positive. So we have n equals 3 is the next one. So a sub 3. negative 1 raised to the 3 plus 1, 2 over 3. 3 plus 1 now gives you 4. What's negative 1 raised to the 4th power? Positive 1. Times 2/3. Does 2/3 reduce at all? And so there you go. What do you notice is happening to the signs of our answers? We'll do one more. They're alternating, aren't they? Why are they alternating?
Because the exponents, like when you add up like each n, like whenever it adds up to an odd number, that -1 remains a negative. But when you add it up to a positive power, it becomes positive.
Exactly. Every time, and what are we doing with that power every single time we're going to the next term? If it's even when n equals 1, that power is even because 1 plus 1 is 2. What type of number is it when I go from 1? Now I'm at 2. So what type of number is it now 2 plus 1? What type of number is that? An odd number. So then I move up to n equals 3, which now it's 3 plus 1, which makes it an even number. 4, an even number. 4, term 4 ends up making the power of 5. So every time I increase by term, I am alternating odd and even. Y'all see that? It's the way you count. 1 is odd, 2 is even, 3 is odd, 4 is even, 5 is odd, 6 is even. You see what I'm saying? And that's what's going on here. And that's kind of what Duke was explaining, the fact that every time we move up a term, we're going from odd to even, odd to even, odd to even. Negative to positive, negative to positive, negative to positive. Do you see that? And that's whenever you see -1 raised to a power, you better expect it to alternate signs. It's going to alternate signs every time. That's the reason why in sequences and series we have -1 raised to a power present, so that we can alternate signs. That's the only thing we have that for, okay? Y'all get the idea. I'm not going to keep going to 6 because I really don't have room, so I'll just stop there, okay? So there we go. So it says now write the first 5 terms of the sequence, and I want you guys now to do the same thing. So you have these next 2 to go ahead and plug in 1 through 5 and see what you get for the first 5s of your sequence. You can check your work. Can you say that again?
Like, so when you find your first, like, 2 or 3 terms, is that when you say that, when you know there's a pattern? Because, like, if we just had 6 and 12...
Together, okay? So look at the next one. We're doing the first 5 terms. So if I was to plug in 1 first... So we end up with -3. Yeah, that's a -3. It's pretty poorly written. But -3 times 2/5 raised to 1 minus 1. Well, you see the 1 minus 1, so what happens to this? Turns to a goose egg. Which means 2/5 raised to the 0 power is what? 1, which means that A1 is equal to -3. A2... -3 raised to the, or times 2/5, 2 minus 1. 2 minus 1 is 1. 2/5 to the first power is 2/5. -3 times 2/5. Multiplying whole numbers times fractions. What do we do, guys? Put it over 1 and just multiply across. What's -2 times, what's -3 times 2? 1 times 5. There you go. So now it's 3 minus 1 power. What's 3 minus 1? 2. So we're squaring 2/5. Squaring a fraction means what, guys? How do you square a fraction? Well, what does squaring mean? Period. Multiply times itself. Perfect. So let me multiply the top by itself. So it's 2 times 2. And then the bottom by itself, 5 times 5. There's your new fraction squared. You're basically squaring the top and bottom. Okay, let's just go ahead and set it that way, okay? So now you have negative 3 times 4 over 25. And so you just multiply across. Okay. Stop there. Johnny was asking, when do we need to go ahead and... From there, we could technically we could stop. What are we doing? I know it's hard to see here, but what are we doing every time, really? We're multiplying. Be careful, not squaring it. We go from 3 to 6 to 12. What is that? Not squaring. You think a lot of people, when you double stuff, you guys think sometimes squared, because you think squaring it is adding it to itself, when it's basically doubling it. So we're doubling the top every time. Do you see that? 3, 6, 9, 12. What's the next one, guys? What's the next one after that? Good. And now we go on to say, what are we doing at the bottom every time? Multiplying by 5. So 1 times 5 is 5. 5 times 5 is 25. 25 times 5, 125. 625. Good job. So if you want, guys, you can do the first 3 terms to get the idea of the pattern and then follow that all the way through. All right. Here we go. Class practice number 4. A sequence is defined by 2-digit numbers divisible by 3. Determine the 5th term. Ooh. A sequence is defined by 2-digit numbers divisible by 3. What's the first 2-digit number divisible by 3? Very good. What do you think we do now going forward? Be careful, because I thought the same thing. Because I was going to multiply times 3, because I was going to get 36 and stuff. I was like, wait, I just missed a whole bunch of other. What do? You add. Right? Would you agree if I take a number and just keep adding 3 to it, I'm still getting numbers that are divisible by 3? Yeah.
Be wrong if you multiply by 3.
Yes. Your sequence would be incorrect. And it'd get pretty ugly pretty fast. Divisible by 3 means you just remember, because you guys, and I see some of you guys, do this. If I asked you 6 times 8, I've seen some of you guys do this, and I'm wondering, I've asked, like, what are you doing? They're like, I'm counting by 8 6 times. I'm like, oh. That's another way of, that's multiplication, isn't it? 6 times 8 is actually 8 plus 8 plus 8 plus 8 plus 8 plus 8. So when I talk about divisible numbers of 3, basically all I'm doing is taking numbers and adding 3, adding 3, adding 3, adding 3, adding 3, right? That's the same idea. Same idea. All right, determine the sequence from the pattern. So now it's reverse. Now they give us the number, and we've got to go ahead and determine the sequence. So we've got to come up with our equation from it. So, what are we doing? 2, 5, 8, 11. What's happening there? Plus 3 every time. If we're adding 3 every time, just a side question here. If we're adding 3 every time, why aren't these numbers all divisible by 3? What? It started at a number that's not divisible by 3. Good. Okay, that's exactly right. If I started at 3, I'd have 3, 6, 9, 12, 15, right? Fortunately, I'm starting at 2, which is not divisible by 3, so adding 3 doesn't help at all. It just keeps us being short by 1 number, right? 2 short by 1 number to getting to that 3 mark. So 5 short 1 number, 11 short 1 number, so forth and so on. Okay, so we're adding 3 every time, guys. In math, in Algebra 1, guys, where did you put this constant rate of change? Where was that located? What was it called? What did you call that constant rate of change? Well, that's for something different. That's for direct and inverse variation. I just said it earlier, except we reversed it. What's that called when you're adding a number every time at the same time? Ratio, rate of change, which also is called, it's one word, starts with an S, rhymes with slope. Good job. So there we go. There's our slope, right? Slope is constant rate of change. So 3 times n. Now here's the deal is, where did we start off? At 2. But you got to be careful here, because if I do this, what's wrong there, guys? No, that'd be the next thing. We'll get to that one in a second, Mason. You're jumped ahead, huh? If I put in plus 2, the number we start off with, because don't we talk about slope and y-intercept? We talked about that, right? This is the slope, so the number we start off with should be that. And you're right. As soon as I plug in 1, what's wrong here?
And should it be 3 and minus 1, so every time it like... No, wait, no, I'm screwing up.
It's okay. No, you're fine. It's, what we're defining is what is that number? What should we start off with? And yes, it should. You're actually right.
Oh, I
No, you're right. Bless you. But here's the problem. As soon as I plug in 1, which we're supposed to do, if I plug in 1, guys, we should get 2. Are we getting 2? No. So if I plug in 1, Sean, what should I put here in order to get 2? Right. Minus 1. Guys, how did we get minus 1? Look at this sequence. Look at the series. Look at the question. Where would minus 1 be located? The very front, as in like before we just started it. The number right before we started our sequences would have been that minus 1. What term number is that? Good. 1 second, Michaela. I'm almost done here. What's y-intercept defined as? What's y-intercept defined as? Crosses the y-axis. What's true about the x value when it crosses the y-axis? X equals 0. Right? So if you want this constant here, guys, in your equations, you've got to figure out what's the 0 term. This represents a sub 0. This represents that difference. Y equals mx plus b. B is a y-intercept, right? Y-intercept's when x equals 0. This is 0. I'm just trying to make, what I'm trying to do is make connections of Algebra 1 to this sequences and series stuff. Okay? And we'll get to the, there's actually a formula, guys, that will be given to you that you can plug right in. And you'll get it in just a second, okay? All right, so now, and this is what Mason was bringing up earlier, now let's talk about this one. Is there a constant rate? Am I adding the same number every time? No, what are we doing every time? It's a constant ratio. Right? So let's talk about constant ratios. There's a constant rate, which is that y equals mx plus b. Now let's talk about constant ratios. What are we multiplying every time? 3. What is it called, guys? We just took a test over it. What type of function is it where you take this number and you multiply it times itself over and over and over again? What's that called? Exponential. Do y'all remember what exponential looks like? Yeah. It's usually some number times another number raised to some power, right? It's kind of what we had last test and stuff. It was a little bit elaborate, more elaborate than that, but that's kind of the basic, the foundation of it. So we need to take some number and then multiply it by the same number over and over and over again. What's the same number we're multiplying over and over and over again, guys? 3. So that goes there. Is that right? So, we've got to put a number in front. Well, what number did we start off with? Okay? So we start off with 3. We're multiplying by 3 every time. Do you agree? 3 is the first one. Times 3 is 9. Times 3 is 27. Times 3 is 81. We're starting with 3 and we're multiplying times 3 every time. Okay, so how do I increase the number of times I'm multiplying something? Where would that be located? Yep. Exponent. The exponent, the power. If I follow, remember guys, every term, if I'm going along on terms, I'm increasing by 1 every time. First term, second term, third term, fourth term. I'm increasing by 1. Which if I use that as a power, guys, that means I'm multiplying 3 one more time. Go from second to third, I'm multiplying by 3 one more time. Because I've increased by 1 term number. I went from 2 to 3. Now I'm not squaring 3 anymore, now I'm cubing 3. Fourth term, I'm raising 3 to the 4th power. Fifth term, raising 3 to the 5th power. Or, yeah, so forth and so on. Whatever. However, there's one little thing here. Same thing as the previous problem. What would my first term be? If I followed this formula right here, guys, what would my first term be? Not 3. So what do you think we have to do here in order to fix this? Don't change the 3. Be careful. Because you what?
It still works.
This one?
No, the other one.
This?
Yeah. If you change it to 1, it still works.
To 1? Okay, and you're right. And that would work perfectly fine for, but here's the deal. This worked out great because these two are the same number. That would work out. Sometimes it's not. The one up here we did was 6 times 2 raised to a power. Be careful. It would work for this one example, Johnny. However, I know there's other questions that won't work. We've got to come up with something a little bit more general. That's a very specific fix. Something more general that will fix everything. Okay? If I'm here, guys, if I'm at my second term, because we said 3 times 3, my first term, that means that's 1. 3 times 3, that makes 9. How do I go back one more term?
And you have 1
Where?
on the X.
What variable represents the term number? That would be a general fix. That's how you do constant ratios. It's always n minus 1. It is your initial value, usually represented by A0, times your rate raised to the n minus 1. Sorry guys, I'm going to scroll to the next one and we'll use that so you'll see that equation again, okay?
So that whole thing, that's ready for everybody.
Yep. That equation you just wrote down will be given to you on the quizzes and tests and can be used for quizzes and tests. That is your general one for ratios. That's how you come with the equation for ratios. All right. Find the general terms of sequence with one rule. Okay, so let's look at this one. So they always like to do this. And guys, I know some of y'all, fractions is an F word. Okay? And you want to use the F word when you're doing fractions. Okay? But let me tell you this. When we're dealing with sequences in series, it's basically this. A sequence of numbers on top over a sequence of numbers on bottom. You treat them separately, okay? Don't think them as fractions altogether because sometimes that can get a little confusing. Okay? So, let's look at top here for this one. Is the top changing at all? Okay, so then we can't determine anything from there. Let's look at the bottom. Is the bottom changing at all? What's it doing every time? Is it adding the same or is it multiplying the same? Multiplying by. So for multiplying, we're looking at the equation I just showed you. And let's use that. So a sub n is equal to, what is our first term? 3. What's our first term? 4/3. I know I said keep it separate. When you're finding the pattern, keep it separate. I'm sorry, when you're finding the pattern, keep them separate. When you're putting the answer, you have to put 4/3 in. We're multiplying the bottom by 3, but what are we multiplying the top by? Good. You agree? It's 4/3 is your first one, and all you're doing is multiplying the bottom by 3 every time. Does that fit? That fits.
What about the n-1?
The n-1 takes care of the very first term, Johnny. Because first term, n equals 1, right? If I was to plug this in and check it, one minus 1 is 0, which means 1/3 to the 0 power is 1. The n-1 will always be, that's why you always put the first term in first and multiply it times a constant rate. Because when you put n-1, every single time your first term will always end up raising to 0, which makes that rate being just 1. And you're multiplying by 1. So that's why it always works. So there's your first term. All right. Next one. What are we doing at the top? Adding by. This is kind of backwards examples, huh? How about the bottom? Same thing, right? So, the top is adding by 1. The bottom is adding by 1, correct? So, like we did before, your rate of change is going to be 1 on top and 1 on bottom. You can. I'm just doing this so you can visually see what's going on there with that, okay? Now, if the bottom was increasing by 2 every time, it'd be 1/2, right? Again, as you see it, guys, we're treating the top separate from the bottom. I'm saying, what's the top increasing by? What's the bottom increasing by? There's my new rate of change, my new slope. Now, we come off to the end here and we say, okay, I need to go ahead and add, but the problem is I need to add the term that is right there before we started. So how do I go back on both of those? Good. You subtract 1. If we're going to the right, we're adding. If you go to the left, you're subtracting, right? Correct? So if we go to the left and subtract 1, what happens to the top? 0. What happens to the bottom? 0/1, right? So it ends up being just 0. Does that work? It doesn't, does it? So maybe we need to do this. Treat them completely separate. 1n on top over 1n. When we subtracted 1, what did we end up getting, guys? Would that work? Would that be true? Would the first term be 1/2? Second term, 2/3? 3/4? 4/5? Right? Do you see the difference in what we did there? I'm trying to use the rate of change at first like we did earlier. However, it didn't work. So guess what? I had to do the advice that I gave you guys, which is treat the top separate than the bottom. That's exactly what we did. The top is just n, the bottom is n plus 1. All right, I'm going to have you guys do 7 and 8 and see what we do. Well, somebody get something for 7? I didn't. What's wrong with 7, guys? It's not a constant rate, and it's not a constant ratio, is it? Can I can add 3, and then I have to add 5, then I'd add 7. That's not working. Multiply by, what, 2.5? Then multiply by 2, then multiply by, what, 1.7? And it's not working. So then there's nothing. If you can't add by the same number or multiply by the same number, yes, sir.
I thought it was like, so every time you're adding something, you're going up by 2, because 3 plus 2 is 5, and 5 plus
Yeah, I thought.
Okay,
you could, like,
be careful because what you've done is you're finding second difference.
you can't do that.
You cannot. Wait. We can. We can. Sorry. Second difference. Let's talk about second difference. This is quadratic. Second difference is n squared. Second difference is n squared. Okay, it goes into quadratic. First difference is linear, second difference is quadratic, third difference is going to be cubic. As the differences increases, so does your function. So we're actually taking the term squaring it. Where do you think I got the coefficient of 2 from, guys? What is that constant second difference? 2.
I'm so confused on what
Would you add 1 to the 2?
Well, do what?
Would you add 1 to the 2?
Would you add 1 to it? Oh yeah. I'll get to that in just a second. Yes, I'll get to that in just a second. Yes. Yep. So she's saying we do the finish. This is not finished yet, guys. I'm not finished with this just yet. Okay. Right now we're doubling it, and so we go through. Okay, the first term. So for n equals 1, 1 squared is 1 times 2 is 2. That works. Okay. So let's go into the next one. 2. 2 squared is 4 times 2 is 8. Does that work? No, it's not. So we got to figure something else out. Maybe this times 2 is not working. So let's take it out. If I take 1 and square it, if I take 1, I'm plugging it in now into the equation, square it, what do I got to do in order to make it equal to? Let's try this. 2 squared plus 1, is that 5? Huh? It does. 3 squared plus 1 is 10. 4 squared plus 1 is 17. There's our answer. Second difference. Here's the secret. Find what the constant difference is. Write that out. And then go through and plug it in and see if you can get that next one. Yes, ma'am.
But you wouldn't use the 2 at all?
No. I put it in there because sometimes you do, sometimes you have to. So I plugged it in the first time, Mason, and you saw it didn't work. So just remove the 2 and just there.